Hello everyone. So in this example I want to look at an application of the Nernst equation, and we're specifically asked to calculate the potential delivered by a voltaic cell using the following reaction if all dissolved species are 2.5 times 10 to the negative 2 molar and the pressure of hydrogen is 1 bar. And then we're given a reaction equation. Alright, so the first step of course is to figure out what are the half reactions that give this full reaction equation. And if you look up, so there's, you can look in the appendices of a textbook, wherever you would like to look it up, but you can see that the zinc is oxidized, and the zinc oxidation reaction, if you look that up, you will see that it is zinc solid reacting with 4OH minus aqueous, which produces the zinc hydroxide complex plus 2 electrons, right? That's our oxidation reaction, and it has a half cell potential, standard electrode potential of minus 1.22 volt. And our reduction reaction that we're interested in is 2H2O liquid plus 2 electrons need to give us H2 gas plus 2OH minus aqueous. And if you look up its half cell potential, you should see 0.8277 volt. Alright, good. And we just check if we add these two equations together, alright, that we get the original equation. So the electrons cancel, we see that, and we see that there's 4OH on the reactant side, minus 2OH on the product side, leaving us with 2OH, and then we can add, so if you add everything together, you're left with 2 water, you're left with zinc solid, 2OH minus aqueous, and that forms hydrogen gas plus zinc hydroxide. Oh, what did I write there? That should just be like that, sorry. And then 2 minus, like that. Alright, that gives us the full equation. So that is what it is. Alright, so that means it has a standard cell potential, alright, E cell, which is of course equal to that of the cathode minus the standard cell potential of the anode. What happens at the cathode? Well, reduction happens at the cathode, oxidation at the anode. So in other words, if we put the reduction potential at the cathode, that is minus 0.8277 volt minus 1.22 volt, and then we should get 0.3923 volt. Yes, it is a voltaic cell. This is larger than 0, so it is a spontaneous cell, so it makes sense that this is positive, right? If we did it oppositely, we would have gotten a negative value, so then it would have been an electrolytic cell, and that wouldn't have made sense. So we're told it's a voltaic cell, so this is correct. All right, but then we're specifically asked to calculate the cell potential when we have specific quantities of the dissolved species and the gas pressure. So what we're actually asked is to use the Nernst equation and to get the cell potential, not the standard cell potential. So we need to use 0.0592 divided by 2 log Q. And what is Q for this reaction? All right, let's write Q for this reaction. Well, that is quite a thing to write, because the products in this case, firstly, are this zinc. So the concentration of this zinc ion, so zinc OH4, so it's the concentration of that multiplied with the partial pressure of H2 divided by OH minus squared, right? Because those are the only things that have anything. So this is an aqueous solution, so it has a concentration. It's a gas, it has a partial pressure. This reactant has a concentration, stoichiometry squared, and this is a solid and that's a liquid, so they're not included in our reaction quotient. All right. So then if we calculate the standard cell, or the standard cell potential, we calculated just now, so that's 3923 volt minus 0.0592 over 2, and then log of our reaction quotient. Now we're given the quantities. We're told any dissolved species has a concentration of 2.5 times 10 to the negative 2. So these two concentrations are 2.5 times 10 to the negative 2 molar. And the pressure is 1 bar. So we can put that in. So it's 2.5 times 10 to the negative 2. Pressure of 1 bar. And then it becomes 2.5 times 10 to the negative 2 squared. And calculating this gives us 0.34 volt. All right. So that is the cell potential when we have these actual conditions or these actual concentrations. And it actually kind of makes sense. I mean, these are not it's slightly lower than the standard cell potential, because we have our concentrations are slightly lower than what they should be. So we've already moved away a bit from the what do you call it? There's already some of the cell being used up, and it's no longer going to output as much voltage as it should. So we're slowly heading towards a point where the cell has been used up. The battery, so-called, is being used up until some point where it's going to kind of be completely used up. All right, but yeah, that's the point of this example, is to calculate the E cell, which is of course actually just giving you an indication of, is the cell still operating spontaneously? Is it still delivering a potential given a specific combination of the reactants and the products, which is actually just the specific concentrations and amounts available in the cell, the working cell that you have. All right, and we see it still has, so this cell is still operating at the moment. All right, good. I'll see you in the next example.